jungle.
Assalamualaikum and hi, my name is SHAHMI bin Abu Zahir. So today I will explain about the solution of question 1a. So let x1, x2 until xn be a random sample of size n from a normal distribution with mean 0 and variance theta plus 1. Find the distribution of a new random variable y equal to x squared 1 using the moment generating function technique. So from the solution, we know that x is follow the normal distribution with mu equal to 0 and sigma square equal to theta plus 1. So by using the moment generative function formulas, is equal to e exponent to the power of ty. And when we put it into the integration, we will get the value of integration of ety times fy dy. Then we substitute the value of x squared into the y and gain the PDF of normal distribution into the fy. And we will get the integration of e to the power exponent to the power of tx squared times 1 over square root 2 pi sigma squared times exponent to the power of 1 over 2 sigma squared times x minus mu squared. And then we insert the value of mu and sigma square into the equation, and we'll get the integrations of exponent to the power of tx squared times 1 over square root 2 pi theta plus 1 times e to the power of 1 over 2 theta plus 1 times x squared. Then we multiply the exponent, and then after we simplify it, we will get the integration of 1 over square root 2 pi times theta plus 1 times the exponent of negative x squared, the power of negative x squared times t minus 1 over 2 t theta time plus 1. And then we simplify, and then to make it in a normal PDF of normal distribution, we need to multiply it with square root 2 with 1 minus 2t times theta plus 1 to the power of negative 1, and for both denominator and numerator. And we will get the square root 1 minus 2t times theta plus 1 to the power of negative 1 times integration of 1 over 2 1 over square root 2 pi times theta plus 1 times 1 minus 2t times theta plus 1 to the power of negative 1 times exponent 1 to the power of x squared over 2 times pi plus 1 over 1 minus 2t theta plus 1. And we after simplified, we can cancel out the integration, and it will get equal to 1, and the equation is equal to square root 1 minus 2t times theta plus 1 to the power of negative 1. And from the equation, we can conclude that the y is following the gamma distribution with value of alpha is equal to 1 over 2, and our beta is equal to 2 times theta plus 1.
Next, I will explain about question B. The question B asks use the result in A to find the distribution of a random new variable W equal to summation of xi square over theta plus 1, and hence state the distribution of w and its corresponding parameter. So firstly, we need to find the moment of w, which is expected of e to the power of tw. We will replace the value of w, which is the summation of xi square over theta plus 1, from I equal to 1 to n. So the expansion of summation of xi square would be x1 square plus x2 square plus xn square. And from the expected of e to the power of t over theta plus 1 times x1 square plus x2 square and plus until xn square, we will get the moment of MWT. From the result in A explained by my partner Ahmad SHAHMI, we get the distribution of gamma, which is bracket 1 minus 2t theta plus 1 bracket power of negative 1 over 2. And by inserting the equation of gamma into our MWT, we will get the answer value of bracket 1 minus 2t theta plus 1 bracket to the power of negative n over 2. We also know the chi-square of MGF is bracket negative 1 minus 2t power of negative v over 2, and the chi-square function is x square with degree of freedom v. So, comparing the chi-square MGF and our answer, we will know that the distribution of w is chi-square function, which is chi-square with degree of freedom n.
So let's move on to the next question, which is question 1C. Based on B, construct a 1 minus alpha times 100% of confidence interval for theta. So as we know, the theta is included in the value of estimation of variance. So we use the formula and we will get the equation equal to probability of chi square 1 minus alpha over 2n less than w less than chi square alpha over 2n equals to 1 minus alpha. Then we substitute the value of w with a summation of x squared I over theta plus 1. Then next we need to multiply both sides with summation of x squared I divided with summation of x squared I, and we will get the probability of chi squared 1 minus alpha over 2 n over summation of x squared I less than 1 over theta plus 1 less than x squared alpha over 2n summation of summation of x squared I equals to 1 minus alpha. And to put the theta plus 1 from denominator to numerator, we need to change both sides, change the denominator and numerator values for both sides, and we need to change the direction of equality. So we will get the probability of summation x squared I over chi squared alpha over 2n less than theta plus 1 less than the summation of x squared I over chi square 1 minus alpha over 2n. Then we need to minus both sides with 1, and we'll get probability of summation x squared I over chi squared alpha over 2n minus 1 less than theta less than summation of x squared I over chi squared 1 minus alpha over 2n minus 1. And we will get the confidence intervals is equal and to the summation of x squared I over chi squared alpha over 2n minus 1 less to summation of x squared I over chi squared 1 minus alpha over 2n minus 1.
For question D, if summation of xi square is 1000, n is 10 and alpha is 0.05, find the interval estimate for theta. So from the derive of 1 minus alpha 100% confidence interval explained by my partner, we will use the formula to answer the question D. We will substitute all the value into our formula. But remember, for left side of value of new alpha is alpha over 2, and on right hand side is 1 minus alpha over 2. By referring the table of chi-square, we will get the value of chi-square distribution. Alpha 0.05 is 2.483 and chi-square alpha 0.975 is 3.247. So for 1000 over 20.483 minus 1 is 47.8210, and 1000 over 3.247 minus 1 is 306.9766. Thus, the interval estimate for theta is between 47.8210 and 306.9766. And that's all from us. Thank you.